Okay, 2.2 is about the algebra of functions. So again, we're still just reviewing some algebra techniques here that you saw probably in college algebra, and some of these you saw way back when in Algebra 1, intermediate, beginning, whatever that was for you. So we're going to talk about combining functions today, composing functions. So we'll be combining them using sum, difference, product, quotient. We're going to talk about composite functions. We'll do some applications, and we'll even talk about something called the difference quotient, which you have seen before. They're a little bit of work, but I find that they're a lot of fun. So let's talk about combinations of functions. By the way, remember, all of this stuff is going to be coming up when we are especially getting into those derivatives and working with applications of derivatives in chapters 3 and 4, where you're going to have to be able to work on all these algebra concepts just very quickly, where these are just a part of the bigger problem. So for your combinations of functions, you can do a couple different things. You've seen this before. Maybe this notation doesn't look very familiar to you, but you can add or subtract two functions together, and that just looks like the addition or subtraction of two functions. You can multiply two functions, f and g, just by multiplying the functions together, and you can divide them, provided that the denominator is not equal to 0. We talked last time about how a denominator of 0 would make the function undefined. The domains of these combination functions are the intersections or overlap, what's common to both domains of the domains of f and g. Now, for a composite function, so the idea here is you're taking f of g of x or g of f of x. And sorry, I have to move this. There we go. Get my setup here. A lot of times you'll see this written. Sometimes students call it fog or goff. You call it whatever you want, but I always end up rewriting these composite functions as f of g of x or g of f of x. So the way that we would write this in English words would just be f of g of x. So instead of just evaluating a function at a numerical value, you're evaluating it at another function. The note here is that the domains are not the intersections like they were with the combinations of functions. In this case, the domains are the set of all x that are in the domain of g and where g of x are in the domain of f. So we're not going to be doing too much work here with those, but it is important to note the difference between the domains of the composite functions and the combinations of functions. So for the first one that we're going to do, example 1, we are going to use the given functions to answer the questions that follow. So I'm giving you two functions, f and g. The function f is x squared plus 1, and then g of x is x over x minus 1. The first thing we're going to do with these functions is subtract them. We're going to find g minus f. Move this over a little bit. Now, when you saw this above, it was written like of x. I mean, that's kind of implied here. You could see it shorthand as just g minus f, or we could just say this is g minus f of x. You decide. So we're going to use these two functions to answer this question, or to combine these two together. So to find g minus f, I'm just going to take the function g, which is x over x minus 1, and subtract off f, which is x squared plus 1. Now, it's really important to note, by the way, that I can't leave my subtraction like this. I'm taking my quotient here, x over x minus 1, and I'm subtracting off this whole entire quantity, x squared plus 1. If I don't put parentheses around it, then it's going to look like I'm adding 1 to it, and that minus sign's not going to get distributed. So it's really important that we remember that anytime we're subtracting more than one term, we have to make sure to put that quantity in parentheses so that that minus sign actually gets distributed to both of those terms in the expression. So technically you might be like, well, can't I leave it like this? You're actually going to have to simplify this to one term in most cases. But that's okay, because we need to practice this anyway. In chapter 4, you're going to be looking at expressions like this, and you're going to be forcing it into one fraction so that you can look at the numerator and denominator separately to work on some other things we'll be doing. So This is sort of a precursor to that. So what we're going to do here is we're going to write the first expression as it is. We're not changing anything there. But what I'm going to do is if I want to combine these two, if I want to subtract them so that I just have one term, I'm going to need to get a common denominator. I can't just add and subtract fractions by adding and subtracting the numerators and denominators. I need an LCD. So what I'm going to do here is I'm going to multiply the second term here, the x squared plus 1, by x minus 1 over itself. And what that's going to do is it's going to create a common denominator so that I can add and subtract, or subtract in this case, with what's happening to these terms. Once I have a common denominator, I can go ahead and combine these. Now here I'm just multiplying. If you want to, since you're just multiplying, you can elongate that fraction bar, up to you. All right, so now that I know that I have the same denominator, I can just combine these two over that one denominator, and I have x minus 1 times x squared plus 1 divided by x minus 1. And then we'll just continue to simplify because we're not done yet. Before you distribute this minus sign, you should multiply. So I'm going to take x minus, and then we'll FOIL here to multiply these two binomials together. So x times x squared. Remember, FOIL is first, outside, inside, last. So we'll have x cubed, and then outside terms give you plus x. Inside terms give you minus x squared. And the last terms give you minus 1. Now I would recommend you go ahead and distribute this minus sign into the parentheses. So you'll have x minus x cubed minus x plus x squared plus 1 divided by x minus 1. And then just go ahead and combine any like terms that you can. In this case, there's not a whole lot that you can do, but you do have an x and a minus x. So those two are going to be additive inverses. They'll cancel each other out. And that will just leave you with negative x cubed plus x squared plus 1 divided by x minus 1. And that is g minus f of x. So even though we were doing something really simple, which was just subtracting these two expressions, it turned into a little bit more work when we realized we had a lot of simplifying that had to be done. The next one we're going to do is for part B. For this one, we're going to take f and divide it by g. And I'm going to leave that notation the way it is this time. I'm going to recall my function f up here was x squared plus 1. And I'm going to divide that by g, which was x, over x minus 1. Now, if it's been a while since you looked at a complex fraction, I'll remind you what a complex fraction is. It's when you have a fraction inside a fraction. So the denominator of this fraction in and of itself is a fraction. There are a couple different ways we have of dealing with these. Sometimes I'll go through and multiply each term by the LCD. But in this case, because we only have just one term in each part of the fraction, we can just invert and multiply, just like you would anytime you were dividing two fractions. So if I go here to, yes, okay. Sorry, my thing always tries to kick me out. I have to figure a workaround for that. All right, so we're going to go ahead and just, instead of dividing this by x over x minus 1, we'll multiply this by x minus 1 over x. Now, this whole quantity in the numerator is getting multiplied. If I don't put parentheses around it, it's just going to look like the 1 is getting multiplied. So the parentheses are going to be really important here because these two are going to get multiplied by each other. And what that's going to look like, and we're going to do a little bit of simplifying to it, but there's nothing too crazy going on, is when we multiply two fractions, we can multiply across, and we can do the same thing in the denominator. So we can go ahead and say that this is just x squared plus 1 times x minus 1 over x, and then we'll just multiply through in the denominator. Did we already multiply this out? Yes, we did. So up here, we already multiplied x minus 1 by x squared plus 1. So we can just reuse that multiplication that we got in here. So this is going to be x cubed plus x minus x squared minus 1 divided by x. Now, this is sort of driving me crazy because when I FOILed this earlier, I kept the FOIL FOIL order, but it's not in descending order. And usually we write our polynomials in descending order, which means that we write the terms such that the exponents are decreasing. So this is fine. It's technically right, but it's going to drive me crazy. So I'm going to rewrite this in descending order. So it looks like this. And that's how we combine two functions using division. The next thing we're going to do, and again, we're keeping these same functions, is we're going to take f of g this way. Maybe. Here we go. So for part C, we're going to take f of g of x. And if you want, we can match that notation. Now, anytime you're given notation for a composite function, my recommendation for you always is to rewrite this using that standard function notation for evaluating a function. So I would not leave this as fog f of g of x with the little circle. I would write this as f of g of x. Now, remember, we're keeping this order because g is the second function. But if g was the first function and you had g of f, we would, of course, switch that order here as well. So it still should, the function on the left should stay the function on the left, so on and so forth. Okay, if you don't remember, I know my functions are on the other side. F of x was x squared plus 1, and g of x was x over x minus 1. So we're going to go ahead and we're going to take our function f, and everywhere we see x, we're going to evaluate it at g of x. Now, composing functions is something where there are some students who are just really good at this, and other students who are just like, I don't get what's happening here. The only thing I can say to do is just practice, 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 because the more of these you do, like eventually it's going to click. And if you're one of those students who does not have a hard time with these, awesome, wonderful. But you know, we're all different. We have different strengths and weaknesses. So I'm going to go ahead and take my function f, and everywhere I see x, I'm going to swap it out with g of x, just like if I was evaluating this at a number, except I'm evaluating it at a function. So my function f of g of x is x squared. So everywhere I see x, I'm going to swap it out with g of x. So I'm going to take g of x squared plus 1. And that's what this is going to look like. If you're kind of like, okay, cool, put a box around it, skip to the next one, you got to simplify these. And it's really just good for us to simplify these anyway. It's really good for our algebra skills. If you're taking a quotient to a power, you can apply that power to both the numerator and the denominator of your quotient. So we can do that to split up this. If you're wondering why we had to do that, well, it's because if I want to combine two fractions, I need to get a common denominator. So I really wanted the denominator to be its own separate exponential expression. Now, the 1 I'm going to change because, again, if I'm going to combine two fractions, I have to have a common denominator. So I'm going to take 1 and I'm going to write it as x minus 1 squared over x minus 1 squared. And now I've just renamed it. Remember that I can simplify this and I'll still get 1. The whole point of doing this is so that I can get a common denominator. And now I can rewrite my expression over this common denominator. Now, notice that I'm not going to rewrite my square, and I'm going to tell you why in a second. I'm actually going to show this being squared. When I square a binomial, I'm really just multiplying it by itself. What I've had a lot of students do, even in Calc 3, I see this. Calc 2 students do it all the time. It's not just, it's not just like lower level algebra students who are doing this. Calc students do this all the time. Here's what they do. they say that x minus 1 squared equals x squared minus 1 squared, which is x squared minus 1. I'm looking at you. Don't do it. It's not true. This is not true. We had a name for this in my summer Calc 2 class. It was called the terrible awful. Actually, there were two things that we had named the terrible awful. And when the other one comes up, I'll remember it. But this is a big no. Oh yeah, the other one was when students took the square root of a plus b, and they said it was the square root of a plus the square root of b. It's not true. When it comes up, I'm going to remind you, but don't do this. Okay, don't do this. It's tempting, but don't do it. It's not true. You cannot distribute the exponent into terms. You can distribute the exponent into factors, which are quantities that are being multiplied. You can distribute an exponent into a quotient, but you can't distribute it into a sum or difference. All right, so that being said, what I'm going to do is I'm going to rewrite this by foiling. So x minus 1 times itself is x squared minus 2x plus 1. Divide that by x minus 1, quantity squared. Now, there's a little bit of work to do, but not much. It's almost done at this point. I have 2x squareds now that I can combine. And then minus 2x plus 1 over x minus 1 squared. And really, that's about all we can do with this one. You can leave the denominator factored because in this case, there's nothing else that you need to combine it with. It doesn't matter to me if you FOIL it out or not. So up to you. You decide. Okay. The last one I want to do in this little space, I should start telling you kind of how many problems I'm putting in here so you have an idea of how much space to use. But the last one is going to be D, and we're going to find, you might be predicting that we're going to do G of f of x, but we're actually going to do G of f of 1. Now, if you would like to find G of f of 1, you can always find G of f of x and then evaluate it at 1. But you don't have to. What you're really being asked to find here is G of f of 1. You have a function G and you have a function f. If you evaluate f at 1, you're going to get a number, and then you can evaluate G at that number, and you don't have to work on any actual composite functions in that case. You don't have to compose one function within another. See what I'm saying? So let's go ahead and pull those functions back up. I rewrote them over here. So what I'm really looking for is first I'm going to find the value of f of 1. And then when I find that, I'm going to evaluate G at that value. So f is x squared plus 1. So I'm going to find f of 1, which is 1 squared plus 1, which is 2. And the next thing I'm going to do is find G of 2, because 2 is f of 1. So if you want, we can just say that f of 1 equals 2. That's sort of like a sub-conclusion. And now we're going to find G of 2. So G of 2, I should say, equals, well, our G function was x over x minus 1. So we'll take 2 over 2 minus 1. And this will be 2 over 1, which is 2. So like I said, you can always, if you would like, find G of f of x and then evaluate that at 1. But if you don't have to, if you don't need it for anything else, it's actually just easier to find f of 1 and then evaluate G at that value. So the difference here was that in part C, we were composing a function of x within another function of x. Whereas for D, we were actually just evaluating that at a real number. Okay. You can check this if you want and practice your skills of composition, and you would find that this is still true, even if you find g of f of x and then evaluate that at 2. I'll leave that up to you. Okay, number 2, we're going to sort of undo a composite function. I really like these undo the composite functions. I don't know why. I like a lot of weird things. Our function h is g of f of x, where, and I'm going to give you a definition for h. So I'm going to say that h of x is equal to 1 over x squared minus 1 cubed. So what we're going to do is we're going to figure out what f and g need to be in order for h to be g of f of x. Now, again, I think it's going to be really helpful for you if you rewrite this as g of f of x. Can't force you to do it, but it's a really good idea. All right, now you're going to have to focus on, first of all, finding the inside function. When you look at these composite functions, you should be thinking about an inside function and an outside function. So in this case, the inside function is the one that's nested inside these parentheses. That's the function f of x. So we're going to look at the function h and determine what the inside function is. Now, I've seen students do these differently. There's not necessarily one right answer. For this particular example, I can maybe think of 2 ways of doing it. But because we're going to be working a lot with composite functions in later chapters, I want to make sure that we really have a good sense for what it means to be the inside function and not just kind of willy-nilly come up with something that also works in this case, but maybe is not as obvious. When I'm thinking inside, a lot of times I'm looking for parentheses. So for h of x, I'm seeing these parentheses around this quantity that's being cubed. And when I'm looking at the parentheses, that's telling me I have a function that's inside of the parentheses. That function would be x squared minus 1. So I'm going to let my inside function f of x be x squared minus 1. Now my outside function is going to basically be like what is being done to the inside function. So we're taking 1 and we're dividing it by the inside function cubed. So if I basically want the outside function to just really treat the inside as though it was just x, what's really happening here is g is just 1 over my inside function cubed. And that's it. And you can always check this. You can always, make sure that when you compose these together, g of f of x, well, g is going to be this big outside function. It's 1 over x cubed, but you're substituting x with f of x. Check. It's the same. So I'm going to put a couple of those on the homework so you can practice it a little bit. I think it's a really cool thing to do, kind of test your knowledge of those composite functions, working with them in a little bit of a different way. Another thing we're going to do is use a graph to answer questions about composite functions. You may or may not have ever done this before, but it is also kind of cool. We're going to do 2 quick questions in here. The first one is going to be find f plus g of 1. So we're not working with a composite in this particular example. We'll do that in B. In this case, we're looking at a combination of functions. So if you're finding f plus g of 1, remember that means that you're looking at f of 1 plus g of 1. That was from, I think, that very first definition on the first page of your notes. So you're going to look at the functions, and these are in color for you. They're labeled here. The blue dashed line is g of x, and then there's a red line that's solid, and that represents f of x. So what we're going to do is we're going to find f of 1. We're going to get a value for that, and then add that to the value for g of 1. Now, f of 1, remember we talked about this last time, is just the y value when x is equal to 1. Same idea for g. It's just that we're going to be looking at the other function in that case. So for f of 1, I'm looking at this function f of x, and I'm looking at what happens when x equals 1. Technically, I know these axes aren't labeled. we'll say that that's 1. And then, of course, this would have to be 4. So just a standard coordinate grid here. So f of 1 would be the y value on the f function when x equals 1. So when x equals 1, I'll go up here to the f of x graph, and you'll get that the value of f of x is 2 at that point. So we'll say that f of 1 is 2. Now I'm going to do the same thing for g. So when x is 1, g of x is also 1. The graph is hitting at this point, which corresponds to 1 on the y-axis. 2 plus 1 is 3. That's it. And the other thing we're going to do is we're going to take f of g of 3. So to do that, we'll rewrite this as f of g of 3. So I'm going to find g of 3. I'm going to get a number, and then I'm going to evaluate the function f at that value. So g of 3, again, this g graph is the dashed one. G of 3 would just be whatever value my graph is on when x equals 3. So when x equals 3, my g function has a value up here at y equals 3. So now I'm really looking at f of 3 because g of 3 equals 3. So if I know g of 3 is 3, I'll swap that value in, and then I just need to find f of 3. So when x is 3, the value of my f function, well, that's the solid red line, is actually here at y equals 0. Okay, so that's how you would use a graph to answer those questions. It's pretty cool. All right, next, we're going to talk about the difference quotient. If you remember it, great. If you don't, fine. We're going to be using it quite a bit in this class, so you're going to get a lot of practice using it, especially in this chapter. I will first explain to you what the difference quotient is. I know it's kind of hard to see this on my camera, but hopefully you have your notes in front of you. Right now, your labels use X. I want to change those X's to A's without making it look super messy. It's only 4 of them. We can use the difference quotient with X's. Right now, we're going to be using it with A. It doesn't matter, but your text uses A. So it's neither here nor there. The difference quotient is the slope of the secant line. And the secant line is labeled here for you. A secant line is just one that goes through 2 points on a curve. So you've got this, I know it's kind of hard to tell which color is which, but you've got this blue curve that's running through, and then there's a green secant line that hits both of those points. So the difference quotient is just going to be the slope of the secant line. We're going to go into more detail about what this means in a later section, but right now I just want to sort of develop this formula for you. If you can imagine, if this value is x and then the y value, the corresponding y value is f of x, well, in this case, we're calling it a and f of a. So the point that we drew here on the secant line for the intersection would be a, f of a, if you were writing that as an ordered pair. Now, the difference between the first x value and the second one is h units. So if the first x value is a, then the next one is just going to be a plus h because we've just moved that over h units. So we can go ahead and write this as a plus h and then f of a plus h. So that would be the ordered pair at that point. Now, if you're wondering why do we need all that, well, it's because we're talking about the slope, And remember, we talked last time about how when you're trying to find the slope, you're going to be using two different points, x sub 1, y sub 1, and x sub 2, y sub 2. So to find the slope, we know that the slope is the difference or the change in y divided by the change in x. Now, if I want to, it does not matter which point is which, but usually we would just say, okay, let's look at these from left to right. And I'll call this point 1, and we'll call the next one point 2. Then I can say that y sub 2 minus y sub 1 is just the y coordinate at point 2, which is going to be f of a plus h, minus the y coordinate at point 1, which is f of a, divided by, and then we'll take x sub 2 minus x sub 1. So we'll take the x coordinate at point 2 and the x coordinate at point 1. Now, there's not a whole lot we can do here, but we can at least look at the denominator and notice that you have a minus a. So those are additive inverses, and we can get rid of those. So we can go ahead and say that our difference quotient is f of a plus h minus f of a divided by h. And if you feel like this is just some crazy, stupid thing you're being asked to do, it's not. You're going to see how this is going to be used later on. But again, in these first couple of sections, we're laying the foundations with algebra so that when we get to the topics that use this, you already know how to use it. And it's not like you're just learning how to do the algebra while you're learning how to do the calculus. All right, B, find and simplify the difference quotient for the following. I'm going to give you one example that goes on this page because some of these are pretty long, and then we'll do another example that goes on the next page, just with different kinds of functions. It depends. Like sometimes you're given different types of functions that work easier with the difference quotient than others. Sorry, I'm like moving this around trying to figure out the best view. So we'll call this I, because we already have 4a and b, so it is what it is. I'm going to give you a function, f of x equals x squared plus 2x minus 3. We're going to find and simplify the difference quotient. Now, you'll notice that you need specifically 3 things. One of those things is f of a plus h. The other is f of a. And then you're going to divide by h. I only gave you f of x. So in order to find the difference quotient, you're going to need to evaluate this function f of x at a plus h and a. So I need 2 of these quantities, and then I got to divide their difference by h and simplify. Sometimes the simplifying is the hardest part, as you know, maybe. I like to do the hardest one first, but you know what? Might as well just grab this easy piece right away. If I already have f of x, well, f of a is just a squared plus 2a minus 3. The next thing we'll grab is f of a plus h. We'll have to create this. You can either use f of a, and everywhere you see a, you can swap it out with a plus h. I kind of like to just go back to this because if you have a and then a plus h, I don't want it to get confusing. So look at your f of x function, and everywhere you see x, you can swap it out with a plus h. So I've got x squared, so that's a plus h squared, plus 2x. So that'd be plus 2a plus h minus 3. Now I have to simplify this quantity at some point. Since I know I'm going to be subtracting these, I probably want to get everything simplified before I put it together. That's just my suggestion to you. So I'm going to simplify this first before I put it into the difference quotient formula. And I want you to remember that you cannot distribute the exponent here. This is not a squared plus h squared. It's a plus h times itself. So let's go ahead and distribute the 2 here. So you have 2a plus 2h minus 3. Now I can go ahead and FOIL. We'll have a squared. And when you're foiling, when you take the outside and the inside, The outsides will give you a times h, and the insides will give you h times a. But multiplication is commutative. I can multiply in any order. So if I have an a plus h and I add that to an h plus a, I really just have two HAs or two AHs. I tend to keep these in alphabetical order. So I'm just going to rewrite this as 2 AH. And then the last terms give you h squared plus 2a plus 2h minus 3. We'll simplify what we can. Notice that for some reason I was expecting to simplify something here because I put this equal sign there, but actually there's nothing else we can do. So that's fine. We're just going to go ahead and write the difference quotient now. This is our preliminary work. These were the initial steps. And if you feel like, wow, we already did a lot of work, yeah, we still have more to do, but that's okay. It's all good stuff. F of a plus h minus f of a. I'm going up here to the formula for my difference quotient. F of a plus h minus f of a divided by h. So what I'm going to do now is I'm going to start filling everything into this formula. So I already said that f of a plus h was this quantity, a squared plus 2ah plus h squared plus 2a plus 2h minus 3. And now we need to subtract off f of a. Now f of a is more than one term. And I already said earlier today that when you're subtracting off more than one term, you need to put parentheses around that term. So we're going to take away f of a, which is a squared plus 2a minus 3. And we're going to distribute that in a minute. But I want to make sure that we see that with the parentheses on it. That's so often neglected, and students are constantly just losing things because they didn't distribute that minus sign. Okay. All right, so we're going to simplify our difference quotient now by distributing that minus sign into the parentheses. We have a squared plus 2ah plus h squared plus 2a plus 2h minus 3 minus a squared minus 2a plus 3 divided by h. Now, if you've done this correctly, you'll notice that the terms in f of a are going to become additive inverses of terms you already have. What I mean by that is notice that you have a minus 3 and a plus 3. And notice you have an a squared and a minus a squared. And notice you have a negative 2a and a positive 2a. Those are all just going to add up to 0, and you don't need to use them in your difference quotient. So let's see what we have left now. I have a 2ah. I have an h squared. I have a 2h. Is that it? Yeah, that's it. 1, 2, 3. Everything else canceled. Divided by h. Now, there's one last thing you need to do to simplify. Notice that every single term here has a common factor of h. I can cancel it out. If you're not sure about when you can or can't cancel between terms, I'll tell you that you can never actually cancel between terms. But as long as you can factor a quantity and then cancel out the common factor, then you can technically, I guess, cancel between terms. All right. So I'm going to factor out the h, and that leaves me with 2a plus h plus 2. And once you factor it out, as long as you can factor it out, then you'll know that you can cancel that common factor. So now we can say that those h's are just common factors. H over h simplifies to 1. Therefore, our difference quotient can be simplified to 2a plus h plus 2. And that's it. There's nothing more we can do here. There's nothing else we can combine. I wouldn't factor a 2 out of 2 terms. I don't know. That's crazy. Just leave it. It's done. Stick a fork in it. I sometimes think, first of all, we haven't talked a lot about terminology here for these polynomials. A polynomial is when you're just taking various positive integer powers of x and that maybe are multiplied by some sort of numerical coefficient and adding them together. So this is a polynomial function. I sometimes think these difference quotient problems are a little bit harder with polynomials just because you end up having to either square or maybe even cube some quantity a plus h. So whereas students maybe don't want to work very much with fractions, you'll find that they aren't as bad when it comes to the difference quotient. So we're going to do one more of these on the other side, this time looking at a rational expression. Rational expressions are written as a quotient of two polynomials. You should have talked about them quite a bit in your Algebra 2 class. So this will be our second example here. We just have one to fit in this space. F of x equals 2 over x plus 1. So we worked quite a bit already with the difference quotient, but remember, I'm looking for three things. I'm looking for f of a plus h, f of a, we're going to subtract off of that, and we're going to divide that quantity by h. So let's go ahead and start finding what we need. F of a is 2 over a plus 1. Nothing too crazy there. Now, f of a plus h is 2 over a plus h plus 1. Nothing too crazy there. So now we're going to take f of a plus h, subtract off f of a, and divide by h. So I'm going to rewrite your difference quotient here. And we'll start combining this. So this is going to be 2 over a plus h plus 1 minus 2 over a plus 1 divided by h. Now, if you're thinking like, ooh, I probably shouldn't put a box around this. You're right, you shouldn't. You should never, ever leave your answer as a complex fraction. Remember, a complex fraction is a fraction inside a fraction. So don't ever do that. Now, it's kind of up to you how you choose to simplify this. I would say maybe combine the numerators as a single fraction. Sorry, I'm running into my document camera here. Combine numerators as a single fraction. To do that, we need to get the LCD, the least common denominator, because I can't subtract two fractions from each other until they have a common denominator. Now, you'll find that in this case, it's actually pretty quick to find the LCD because these are just two completely distinct denominators. So the LCD is actually going to be a plus h plus 1 times a plus 1. That's what I need each fraction to have on it in the numerator, in the denominator. This is what I need each fraction in the numerator to have as its denominator if I want to subtract them from each other. So let's take the numerators, we'll write them as one fraction, and then we can invert and multiply with the h. Okay, so I'm going to take the first fraction, 2 over a plus h plus 1. Remember, I want to have this denominator on it. In order to get that denominator, I like to put parentheses around these because now I'm getting a lot of terms here. I'm going to multiply by a plus 1 over a plus 1. Now I can get that denominator. This minus sign, I'm just going to rewrite. And now the next term is 2 over a plus 1. And if I want to get this denominator, I need to multiply by a plus h plus 1 over itself. And now you can see why I want more parentheses, all the parentheses. I want all of them. They're going to really be helpful. And whatever you do, don't forget, you still have this h in the denominator. Sometimes we get so carried away with the little work that we forget that we still have other stuff going on. It gets lost. Okay, So now we're going to simplify. We have a common denominator, and as long as we have a common denominator, we can just write both of those numerators, or we can subtract both of those numerators from each other and just leave that denominator by itself. I'm kind of thinking about how I want to write this right now. I'm going to let this be the big fraction bar. So we're going to write this as twice a plus 1 minus twice a plus h plus 1. So those are your numerators, divided by your LCD, which is a plus h plus 1 times a plus 1. So all we've done so far, and I still have to think about this h, I haven't forgotten about it, is we've taken the common denominator, we've written it as the denominator here, and then we've combined these fractions in the numerator. So twice a plus 1 minus twice a plus h plus 1. And then instead of dividing by h, we'll multiply by the reciprocal. So if we're multiplying by the reciprocal of h, we're multiplying by 1 over h. Okay, so I know a lot just happened here, but dividing by, if you want to think about this as dividing by h over 1, you're multiplying by its reciprocal, which is 1 over h. All right, let's see what we can simplify here. I'm going to go ahead and distribute and combine whatever I can. I have 2a plus 2 minus, I'm going to just distribute this negative 2 into the parentheses. So we have minus 2a minus 2h minus 2 divided by a plus h plus 1 times a plus 1. And then I have this h here. I'm just multiplying, so I might as well just move it into this denominator. If I'm multiplying, I can just multiply across. And then we'll just simplify whatever we can. So I have a 2a and a minus 2a. And then we have a 2 and a minus 2. Now, when I rewrite this, you're going to notice that we're going to get an h that's going to cancel out. But I'm going to wait on that. A plus h plus 1 times a plus 1 times h. And once you get to that point, you're like, okay, got it. There's clearly a common factor of h. We know it's a common factor because it's just getting multiplied by all the other factors in the denominator. And we'll simplify this one more time as negative 2 over a plus h plus 1 times a plus 1. Don't bother expanding that. It's good just like this. By the way, when I had your notes made for this class, I requested that they leave them single-sided, which is an odd thing because I know normally we like to save paper, but I know sometimes I have some students who just write a lot larger and need more space. I have some students who will write this whole example in half the space. But if you need more space, that's why I left the other side single-sided so that you could use that in case you needed some overflow space. All right, last one for this lesson is kind of a precursor to what we're going to be doing in 2.3, which is going to be just lots of application problems, nothing too crazy. We're going to be doing a little bit more work in 2.3 with some things like supply and demand and just interpreting word problems and turning them into actual mathematical functions ourselves and working with functions that are given to us. So this is sort of like a little bit of an intro to what we'll be doing in 2.3. Another thing that you're going to see in this problem is revenue and cost and profit. And these topics are going to come up throughout the entire class. They're not going anywhere. You're going to see them even in chapter 6. So don't get too lazy about it and think, I'm not going to see it again. You'll see them. They'll pop up throughout the class. It's business calc. Of course they will. A company manufactures cell phones. The weekly fixed cost is $20,000. The variable cost for producing X phones per week is V of X equals this function in dollars. The revenue from selling X phones per week is given by this function. Assuming that the number of phones you sell, X, is between 0 and 7,500. Now, it's important for us to talk about what some of these quantities mean. Like, for instance, fixed costs are $20,000. Now, these are independent of how many phones you produce or sell. Fixed costs might be just your payroll, how much you have to pay the employees. I mean, you still have to pay them regardless of how many phones you sell or produce. Maybe even the facilities that you maybe rent or you're paying off, or just the cost of keeping those facilities running, the machines. Fixed costs are just costs you have to pay regardless of the number of phones you sell. You might have a really bad month, but that doesn't mean that you don't have to pay to air condition the building that everyone's making the phones in, something like that. The variable cost is going to change. Variable means it's changing. And that's going to be based on the number of phones produced per week. So you'll have two different costs here. One of them is fixed. The other one is variable. You know, if you produce more phones, it's going to cost a little bit more money to make them. The revenue from selling a specific number of X phones is given by this function. So the first thing we're going to do is find the total cost function. So remember, I already said that we have a weekly fixed cost and a variable cost. So the total cost function is going to be a combination of those two functions, and we're going to combine them using addition. So we're going to take the fixed cost and add it to the variable cost. And then we'll just take those two functions and add them together. And a lot of times we just label the cost function as C of X. So this is just going to be, and you can do this in any order, but since the fixed cost is just a constant, I might pop that onto the end. So maybe you switch this order, but addition's commutative, so we can do that. We'll just take our variable cost, 1, 2, 3, 4, 5 zeros after the decimal, minus 0.01 x squared plus 50x, and then add the fixed cost into that. So this will be your total cost function, just those two costs added together. Find the profit function. So the profit and the revenue are not the same. The revenue is the amount of money you're bringing in for selling those phones. But remember, you still have to pay to make the phones, and you still have to pay your fixed costs. You got to pay your employees. So you're not just getting all that revenue and profit. Yeah, they're selling the phones, but you're not just pocketing all the money. So you have to think about the revenue taking away then the cost. So the profit function, the profit is the revenue minus the cost. So a lot of times you'll see this in function notation as P of X is R of X minus C of X. But I feel like this is pretty intuitive for people. You guys have generally a very good understanding of, I don't know, the whole idea here between producing things, even if you don't do it yourself, and selling things. All right, so we're going to take our P of X, and we're going to say that P of X is equal to the revenue minus the cost. So our profit function is the revenue function, which is negative 0.02x squared plus 150x minus the cost. Don't forget your parentheses. We're subtracting off more than one term. So we need to make sure that we distribute that negative. Otherwise, if you don't, they will fire you and get a new bookkeeper because you've messed up their profits. And there's nothing they hate more than having some low-level bookkeeper mess up their profits just because they didn't distribute a minus sign. So it makes a big difference. All right, negative 0.02x squared plus 150x minus 0.023451x cubed plus 0.01x squared minus 50x minus 20,000, which makes sense. You knew that 20,000 was going to have to come off at some point in some way. Oh, am I really calculatorless right now? Please say I'm not calculatorless. The girl who owns like 50 bajillion calculators. Hold on, I got one real close by. Real close. It's super close. Two of them. Right. We're good. Just put this into your, oh, what am I putting? Oh, yeah. Well, actually, I don't really need to put much into my calculator. I only need to combine like terms. So there's not really a whole lot to do here. But I'm going to take the negative 0.02 for the x squareds, and I'm going to add 0.01 to that just to get negative 0.01. So we'll combine those terms. There's nothing to combine for x cubed. I'm going to write my coefficients in descending order. Okay, so for the x squareds, when we combine this, we get minus 0.01 x squared, and then we'll have 150x minus 50x, so that's plus 100x, and then minus 20,000. So that is your profit function based off of selling and producing X numbers of phones. All right. What is the profit if 2,000 cell phones are produced and sold in a week? Well, that would be P of 2,000. So we already have the P function. So you're going to have to go in here and figure out what P of 2,000 is. Let's see if I can fit this in here. Calculator. Whether or not you can see it is going to be a whole nother story. We'll see. So I've got negative 0.12345 times 20,000. Oh no, 2,000, not 20,000. 2,000 cubed. So I'm just everywhere I see X, I'm swapping it out with 2,000 minus 0.01 times 2,000 squared. And then plus 100 times 2,000 minus 20,000. And you should get 132,000 dollars. Anytime we're talking about applications, we want to use units, and in this case, it's dollars. I guess technically you could write dollars, but you could just use the dollar sign. But you know what? Popping all that into my calculator just sort of reminded me. You know, we'll talk about it another day because you probably won't use that for this anyway. We'll talk about it another day. If you have ever used the variables and the y bars in your calculator, we're going to use that when we talk about limits, but I don't think you would use it for this, so not too worried about it. All right, so that is all I had to say about 2.2. Next time we'll talk about 2.3 and build some mathematical models and use supply and demand and talk a little bit more about profit, revenue, and cost. That is all. I'm going to stop my recording.